Okay, so we're recording. Welcome back, everybody. Hope you had a good weekend. Today what we're going to be doing is starting a new chapter on kinematics in 2 dimensions, but before we do that, I'd like to make a few announcements. As usual, we have a new homework assignment, which will be due next Tuesday. It's up here on the board. You can also find it on Canvas. Make sure you get a copy of this worksheet at the front of the room. That will be part of the assignment. Also, just to let you know, we are going to have another quiz coming up soon on Thursday. So it'll work pretty similarly to how the first quiz was at the beginning of lecture. When you get here on Thursday, we'll take the quiz. It should take about 15 minutes to complete. And the topic, just so you know what to study for, is going to be kinematics in 1 dimension. This is material that we haven't been talking about in lecture for a little while. But as you remember, we went through kinematics in 1 dimension in weeks 2 and 3 of class. Okay? Any questions on that stuff? Okay, next announcement is about the upcoming test. So the very first test of the semester is going to be given during your lecture on Tuesday, February 22nd. So all we're going to be doing on that day in lecture is taking the test. You'll have the entire period to complete it, so that's about 1 hour and 20 minutes. Here's what you can expect to appear on the test. There will be anywhere between 5 and 6 problems. I haven't decided yet. And they will all be in a free response kind of format. So there's no multiple choice or anything like that. I'm really just interested in how you show, excuse me, how you show your solution and justify all your work to each problem. Here's what's going to be covered. We're going to cover chapters 1 through 4 of our OpenStax textbook. And just to remind you what those chapters entail, the first chapter was on measurement. The second chapter was on vectors. The third chapter was kinematics in 1 dimension. We've covered all of that already. The last chapter that's going to be covered on the test is kinematics in 2 dimensions. And that's what we'll start on today. And we'll be covering that until the day of the test. All right? Here's what you can bring on the day of the test. This is important to make sure you're prepared. Of course, you can have a calculator. You'll need that to make certain computations during the test. But also, you can bring a cheat sheet. And so here's what the cheat sheet is. It's just a half sheet of paper that you create, and it's filled out on the back, front and back side with your own notes. All right, so you get to decide what's on your own cheat sheet. It's a personal cheat sheet. And I honestly don't care what you put on your cheat sheet. It's really up to you. But what I would suggest is review all of the chapters, all of the lecture notes, and try to condense everything into something that you can put on to have a sheet of paper front and back. So all of the important equations, like the kinematic equations, for instance, will certainly be on your cheat sheet. Okay? Any questions on that? Go ahead.
Is there still a lab that day? Or?
There will still be a lab that day. We'll have a lab as normal after the test. Yeah. And then next week in lab, speaking of lab, we're going to go over some review problems to help you prepare for the test. So I've already posted the test 1 review packet up on Canvas. Has anyone taken a glance at that yet? Okay, so you can find that on Canvas. I'll give you a printed copy next week, but you can start working on it right now if you want to. We'll spend next week in lab going over these problems. It'll be a good way to help you prepare. So you'll do a combination of going through the problems in this review packet. That'll help you study. Remember, I have end of lecture problems, which you can also use for practice to help you study. And creating the cheat sheet itself is actually a good way to study because, again, it forces you to go back through all the material that we've covered so far and try to condense it into a way that's understandable to you. So just the act of preparing a cheat sheet is actually the process of studying. So any questions here? All right, so let's jump back to the lecture. So what we're covering today and what will be on for the next 2 weeks is kinematics in 2 dimensions. So essentially what we're doing here is we're combining ideas from chapters 2 and 3. Ideas of vectors with ideas of kinematics and trying to merge them together. This is covered in chapter 4 of our textbook. So that's where to do the relevant reading. Okay. The first thing we need to cover when it comes to kinematics in 2 dimensions is to go back to the very beginning and just define some quantities. Position, displacement, velocity, and acceleration. But the idea here is now we want to think of all of these things explicitly as vectors. So let's see how we can define these quantities as vectors using some of the mathematics we developed last week. Let's start with position and displacement, okay? So when it comes to position, we could be in a 1D coordinate system or a 2D coordinate system or potentially even a 3D coordinate system. Let's be as general as possible and say we're in a 3D coordinate system where we have the axes x, y, and z shown here. So the position as a vector is a vector that goes from the origin, that's where it starts, and then it ends at the location of your object. So if you imagine a vector just going from the origin out to the location of some object, that would be the position vector for that object. And so the way we can write this in terms of the x, y, and z components is just this. You say x I hat, x is just where the object is along the x-axis, plus y j hat, y is just the coordinate telling you where it is on the y-axis, plus z k hat. So it's x, y, and z coordinates, but this is how we explicitly write it as a vector. Make sense? Okay, displacement. We know what the definition of this is already. It's really the same thing as before. It's a change in position, right? But now when we think about position changing, we have to think about that as being another type of vector. So let's just write it out this way. If r is the symbol I'm using for a position vector, okay, then delta r is a displacement vector. And it's really just r final, whatever my final position is, minus r initial, okay? But what I want to show you real quick is that this delta r displacement thing actually points from your starting position and then it ends at your ending position, okay? Can you see why that is just from the equation? If not, I'll show it to you this way. Okay, you see delta r equals r final minus r initial, right? I could slightly rearrange that to say r final equals delta r plus r initial. In other words, just imagine throwing the r initial to this side of the equation and it's being added, right? So that's like saying, to get my final position, I'm just taking my initial position and then adding some displacement to it. That's just another way of thinking about what this is saying. So if this is my initial position, I've got a vector going like this, right? And then I have to add some vector to that to get to my final position. That's my delta r. And when I add these two together, I get my final position. So just think of it as, to get to my final position, I start with my initial position and then I add some kind of displacement to that. So that displacement is going to be pointing from your starting to your ending position like this. That makes sense? Okay, so that's a feature that we want to recognize. Okay, a little bit more on displacement. So like any other vector, we can break a displacement into its x, y, and z components. So here's what this would look like broken down into component form. We have delta r equals delta x times I hat plus delta y times j hat plus delta z times k hat. In other words, we can just break it down into displacements along each axis, x, y, and z. Okay? So let's take a look at this picture to kind of guide us along. So this is the same thing I showed you before, where we have r initial and then a delta r vector taking us to our final position. Okay? But now what I want to do is sort of break that down by component, right? So if this is my r initial vector, x initial is just that vector's projection onto the x-axis. So that would be right over here. Y initial, that would be that vector's projection onto the y-axis. So that's over here. And then same for the final vector, right? We're just projecting onto x and y. So if this is x initial, this is x final, we've moved some distance to the right in this picture along the x-axis, correct? So we would say we have a positive displacement along the x-axis, right? But if this is where we start on the y-axis and then we end up down here as our final y position, we've moved down, so our y displacement our delta y would be negative. Okay, so the point is, these individual delta x, delta y, delta z things, they can be positive or negative. Just depends which way you're moving along a certain axis. Okay? So if we just write it out by component, delta x is x final minus x initial. Delta y, y final minus y initial. And then same with z. Delta z, z final minus z initial. Okay? Does that make sense? So basically it's the same definition we've seen before, but we apply it to each one of the coordinate directions separately. All right. What about velocity then? We've seen how we can write position and displacement explicitly as a vector. We can do the same for velocity. So again, I just want to go back to some definitions we established in the second week of class, starting with average velocity, okay? So the average velocity is basically a displacement divided by a time. That's the simplest way to say it. So it's a displacement divided by the time it takes to undergo whatever that displacement was. So now, instead of delta x, that's how we would write it if we were just thinking of one-dimensional motion. Now we have a delta r vector, okay? So this is that delta r vector divided by delta t, okay? And that's what we call an average velocity. If we want an instantaneous velocity, that is velocity at a single moment in time, we simply take the limit as delta t goes to 0. And in calculus terms, this gives you what we call a derivative. Okay? We could write this as dr dt. So it's the derivative of my position with respect to time. But that's a vector, right? So let's try to expand this out into components and see what each component looks like. So if I'm taking the derivative of my position vector with respect to time, I'm doing that for every single component. So I would do dx dt. That's my x component. dy dt. That's my y component. dz dt. That's my z component. So the rate of change of my x, y, and my z positions give me my x, y, and my z velocities. So we call this guy vx. That's the x component of our velocity. Okay, the second one we call vy. The third one we call vz. Okay, so again, we're not really going to do any sort of calculations using derivatives, but I just want to show you how to define things in that way. Does that make sense? Okay, what about speed? Do you remember how speed works? Speed is just going to be the magnitude of your velocity vector, okay? Because the idea behind speed is we don't care about direction. We just want to know how quickly you're moving without any regards to which direction you're moving in. So the way that's going to work is it's simply the magnitude of a velocity vector. That's something to remember from here on out. If we ever refer to a speed of an object, you simply take the magnitude of the velocity vector. And like any other vector, here's how it works. You take the square root of vx squared plus vy squared, and actually if you have a z component, that just follows along under the radical plus vz squared, okay? Typically we're just going to work in 2 dimensions with x and y, but again I just want to show you how it generalizes to 3 dimensions. Okay, we all good so far? Let's do an example. Here's the example. We have a radar station which detects a missile approaching from the east. By the way, take a look at the worksheet from the homework. First problem is pretty similar to this. Okay? So at first contact, the missile is 12,000 feet away, and we see it at 40 degrees from the horizon. So our radar dish is pointing at 40 degrees above the horizon to see where the missile is. 2.5 seconds later, the same missile has way changed its position. Now we see it 25,800 feet away at an angle of 123 degrees from where we initially saw it. So we have to turn the dish all the way 123 degrees from where we started to get to where the missile is now pointing. So what we're going to do is find displacement and average velocity for this motion of the missile, and we're going to do it in xy component form. Okay, so we're just applying the definitions, using what we know about vectors to do that. We good on that? Okay, so just so you know what I'm going to write down once it comes to the equations, I'm going to call this direction up the positive y direction, and then I'm going to call this direction east the positive x direction. Okay? So let's work it out. So the first question has to do with displacement. And for this, we're just going to use the definition delta r equals r final minus r initial. And I showed you already, we're going to set up our coordinates like this, where the origin of our coordinate system is where the radar dish is located. Okay? So if I can just write out my vectors r final and r initial, and I can write them in component form, then I could just subtract one vector from the other. We learned how to do this last week, right? So let's start with r final, okay? With r final, we know that we're located 25,800 feet away from the origin. So I'm going to write that number down. And then if I take cosine of the angle off the x-axis that my position vector is oriented at, then I'll get the x component of r final. So do you remember what that angle was in this problem?
40.
So for the final angle, it's actually 123 plus 40 in this case. Because 123 was relative to where you started. 123 plus 40 is how far you have to go off the x-axis in that problem. So we would actually plug in 163 for that, okay? For my initial angle, that's the one that was 40 degrees, okay? Because that's where we started. So for my final position, that's the first one I'm writing down, I have 25,800 feet cosine of 163, I hat, plus, same thing except sine, that will give me my y component. Running out of space a little bit here, sorry. Okay, you see what I wrote down? Hopefully it's clear. Now I'm going to subtract r initial. So initially, we were just 12,000 feet away. And we were off in a direction of 40 degrees. So if I take 12,000 feet, cosine 40 degrees, that will be my x component of the initial position. And then if I add to that 12,000 feet sine of 40 degrees, that will be my y component. So really all I have to do to take r final minus r initial is subtract these two numbers to get the x component, and then subtract these two numbers to get the y component. So I'll just tell you how this works out, okay? We get minus 33,900 feet for my x component. So it's moved a very large distance in a negative x direction, okay? If you do this subtraction here, you're going to find out it's actually just minus 170 feet. So what is this telling us? The missile has moved basically west by this distance, and then it's also moved a little bit down at the same time, but not by much, just 170 feet, okay? So we've answered the first question because we have displacement, which includes delta x and delta y, okay? So the next thing is to get the velocity. Velocity is our displacement delta r divided by delta t. Now this is pretty simple actually. All I have to do is take this vector and divide out a time. And the way this works is I'm actually dividing the time from each one of the components. Okay? you remember what the time is? How many seconds elapsed in this situation? It's 2.5, okay? So I'll write down the delta r vector. We have minus 33,900 feet I hat, minus 170 feet j hat, over 2.5 seconds, right? That's just copying down delta r and then dividing out the delta t. But just so you know how this works out mathematically, you have to divide this time by the, divide out this time from the x component and from the y component. So we have two calculations to do. If you do 33,900 divided by 2.5, you'll get, and then there's a negative sign there, minus 13,600 feet per second in the x direction, and if you do this, you just get minus 68 feet per second in the y direction. So this is Vx, it's the x component of the missile's velocity. It's moving very fast in that direction. And then this is the y component, which is much smaller. It's barely moving along the y-axis at all. Okay, so I just want to make sure we understand how to do this sort of calculation. We good on that? Okay. So if that's the case, we'll keep it moving. And we'll talk a little bit about path, aka trajectory, okay? So if you ever see this term trajectory, that is just referring to the path through space that some object is taking as it's moving around. Oftentimes, what we'll do to sort of depict a trajectory is to do it with a dashed line. And then we'll actually show our object on that trajectory at some moment in time. But what you should be envisioning is it changes its location along that path as it moves, okay? So one thing I just want to convince you of here is that the velocity of an object, the velocity vector v, is always pointing tangent to the trajectory, okay? That's the entire point of this slide, so let's try to figure out why that's the case. So let's just say, for an example, that this is our trajectory, and this is where we're putting the origin of our coordinate system, okay? Right where that dot is. So let's say this is our initial position right here, this is where we start, and then this is our final position right here. So it's two moments in time that are pretty close to each other, because we haven't really moved that far along the trajectory. And as we know, the displacement of the object, this delta r vector, it goes from our starting position, and then it ends at our ending position, okay? And hopefully you can see that it's almost tangent to the path as I'm drawing it here, right? In other words, it's almost hitting this path at a 90-degree angle, but not quite, right? But let's imagine we take a smaller and smaller time interval, right? So then these 2 points would get closer and closer together, right? And the limit where the time interval goes to 0, your delta r vector is going to be pointing exactly tangent to that path. And of course, my delta v vector, or sorry, my v vector, my velocity, is really just delta r over delta t. So if my delta r vector is pointing tangent to the path like this, so is my velocity vector, okay? So you can always use this result in the future, that the velocity of an object is going to be tangent to the path it's taking, okay? Any questions? Okay. So we're just going to keep plugging ahead here. And again, a lot of this is stuff you've already seen. We're just sort of expressing these quantities as vectors. Okay, so hopefully you remember this definition. If we have an acceleration, the average acceleration is defined in this way. Average acceleration is delta v divided by delta t. So it's the change in velocity that an object is undergoing. That's delta v on top, divided by delta t. That's how long it took to undergo that change. Okay? If we want to think of acceleration as a vector, well, our delta v is also going to be a vector in this case. Okay, so that's the average velocity. Hopefully that's looking familiar. Remember, if we wanted, that's the average acceleration, I should say. And if we want to make this the instantaneous acceleration, it's the acceleration at one moment in time, again, we just take the limit as this time interval becomes infinitesimally small. It's approaching 0. And that gives us a derivative. So this is the derivative of our velocity with respect to time. That's how acceleration is defined. But again, we're dealing with a vector here, okay? So let's try to expand this out into x, y, and z components just to see what it looks like. Okay, so we know that acceleration is the first derivative of velocity. This is what it looks like when you expand it out into components. So remember, I explained already that your velocity can have an x component, a y component, and a z component. So if I take the derivative of my x velocity with respect to time, that's going to give me my x acceleration. If I do it with the y component, that's going to give me my y acceleration. In other words, these components of acceleration are just telling you how my x velocity is changing over time, how my y velocity is changing over time, and how my z velocity is changing over time. That's what I'm trying to show you. But a little bit more calculus, just to kind of nail down the idea. Remember that velocity is already a derivative itself, right? Velocity is a derivative of position. So that's telling us if we take two derivatives of position, that's how we get to acceleration. So if you start at position, you take one derivative, you have velocity. If you take another derivative, you're at acceleration. So we can write that like this. For those of you who are in calc, do you recognize this notation here? This is telling you take the second derivative of x with respect to time. This is telling you take the second derivative of y with respect to time. This is telling you take the second derivative of z with respect to time. So just to label these, that's our second derivative. The first component here is ax, okay? We can think of it in either one of these terms, okay? They're both equally valid. This component is ay, and this component is az. So just like any other vector, it has an x, y, and a z component. That's how you want to think about these components, how they're defined, okay? So I know I'm throwing a lot of math at you, so we'll of course get to an example to make this a little more clear. Do we have any questions so far? All right, so the last thing to note is that sometimes we'll have an acceleration vector and we'll want to know what its magnitude is. How do we do that? It's just like taking the magnitude of any other vector that you've seen. If I want the magnitude of A, I take the square root of ax squared plus ay squared plus az squared. That's how it works. That's how it works with any vector. All right? All right, let's try this one. So I want you to try this out. See if you can get this. So we have an object, and it's moving on this curved path that you see here, okay? So what I'm showing you is we start off at this position, and then we end up over here. At t equals 0, where we first see the object, it's moving at 2 meters per second in the y direction, okay? Then at t equals 2 seconds, that's 2 seconds later, now it's over here, and it's moving at 4 meters per second, and it's moving in the negative x direction, okay? So what I want you to do is to calculate the average acceleration of this object, and it's a vector, so you can express it in x, y component form. All right, so basically you're going to find out what is delta v for this object and divide it by delta t. And just, again, keep in mind, this is a vector, it's going to have x and y components. Try it out, see what you get. Okay, let's go through this one. So the first thing I'm going to do here is actually just write out what delta v is equal to. Delta v is our change in velocity. This is going to come into play, of course. We can think of this as v final minus v initial. And now, if I simply write each of these as a vector, I can subtract one from the other. Okay? So what is our final velocity?
4 meters per second.
Okay, and then of course I want to make sure I'm including its directional information. So it's moving in the negative x direction at 4 meters per second. So as a vector, this should be minus 4 meters per second times I hat, correct? That's v final right there. And now what I'm doing is I'm going to subtract v initial. So what was my initial velocity?
2 meters per second.
Yeah, so here, this is what I'm putting in for initial velocity. 2 meters per second j hat, because it was moving in the positive y direction, okay? So if we start off moving at 2 meters per second in the positive y direction, that's our initial velocity. If we end up moving at 4 meters per second in the negative x direction, that's our final velocity. So because everything's just pointing along a single direction, we don't have to go through the work of breaking these up into components, okay? It's just right there. So, what would my average acceleration be? That would be delta v divided by delta t. So I would just simply take my delta v vector, which again is minus 4 meters per second times I hat, and then minus 2 meters per second times j hat. And then I would divide that by, well, it's 2 seconds, right? It's a 2-second time interval. So this is easy to do. We have minus 4 over 2, which is minus 2 meters per second squared. See, we have seconds squared on the bottom now. That's going to be our x component. And then we're going to have minus 2 over 2, that's minus 1, meter per second squared, j hat. So just to be clear, this is what we call ax. That is the x component of our acceleration. What it's telling us is how quickly our velocity in the x direction is changing. That's what that does, okay? And then we have ay. Again, that tells us how quickly our velocity in the y direction is changing. That's the function it serves. If we're dealing with acceleration as a vector, we need both of these pieces of information, okay? Make sense? Again, there's another one on the worksheet that's kind of like this, so hopefully you see how to do it. Okay. Any questions so far? Let's keep going then. Right, so just to summarize, that's all I wanted to say about how to define position, velocity, acceleration in terms of vectors. Hopefully you're getting a sense of that, and of course we'll talk more about it as we go. But position is r, and if I take the derivative or just the rate of change of this thing, I get velocity. V is a vector, so if I take the derivative of that thing, which is the time rate of change, then I get to acceleration. So really that's the whole summary right there. All right, so with that said, now we can talk about our kinematic equations. So you've seen the kinematic equations before. These are not going to be anything new really. It's just that we're going to express them in a different way. We're explicitly going to express them in terms of vectors. Once again, that's the goal of this whole lecture here. So let's just see how that's going to work, okay? If you want to take the kinematic equations that we already know, these are the one-dimensional kinematic equations that we saw back in chapter 3, but you want to now express them in terms of vectors, okay? And what that's going to allow you to do is deal with motion in more than just one dimension. With vector equations, you could deal with 2-dimensional motion, 3-dimensional motion. It's just more general, right? So if that's what you want to do, you basically take the same exact equations that you've already seen, but you make all of the substitutions that I just showed you. Position, that's no longer x, that's going to be a vector r, okay? Velocity, we're not just going to think of like one component, vx. We're going to think of this as a full-fledged vector, v. And same with acceleration. We're not just going to think about acceleration on the x-axis only. We're going to think of this as a full-fledged vector, a. So let me show you how this works with two of our kinematic equations that you've seen before. Hopefully this one right here is looking kind of familiar, right? This says v equals v naught plus at. Right? We've seen that in the one-dimensional case. All I've changed is I've expressed each one of these as a vector. The same equation applies, it turns out. Okay, hopefully this also looks kind of familiar too, right? What is this telling us? R equals R naught plus V naught T plus 1/2 AT squared. All right, how do we interpret all this? Okay, R is our final position, but again, now it's a vector. R naught is our initial position, again, it's a vector. And V naught is our starting velocity, and A is our acceleration. So really, the meaning of these variables is the same, and now we have vectors. One last thing to remember about these equations. These kinematic equations only apply if you have a constant acceleration. So if the acceleration is not changing over time, these equations apply, otherwise they don't. Okay? Any questions on that? Okay. So because we're dealing with vectors, like I showed you in the last lecture, we have kind of two basic approaches we can take. We can either take a graphical approach, where solving a problem relies on drawing a diagram of some vectors, or we can take an algebraic approach, where we're just dealing with numbers and we don't necessarily need to draw a picture or anything like that. Okay? So what I'm going to do here is explain how we can use each one of these approaches for our vector kinematic equations. Okay? So let's start with the algebraic approach. How does this work? Well, basically, with the algebraic approach, we start with some kind of kinematic equation like this that's expressed in terms of vectors. And then what we do is we break it down into different components. So if I'm moving in 3 dimensions, I look at this equation and I realize that's actually 3 separate equations. That's an equation for the x direction of motion, that's an equation for the y direction of motion, and the z direction of motion, kind of condensed into this simple form. I can expand it out this way if I want to. Okay, so we have a separate kinematic equation for each coordinate direction. And the way we want to really keep track of everything that's going on here is to put a little subscript to keep track of which coordinate direction we're talking about. So for my x coordinate direction, I'll have Vx equals V naught x plus AXT. If I have some y motion going on, then I'll have an equation that looks like Vy equals V naught y plus AY times time. In other words, every single term where there's a vector, I just pick out a certain component. Okay? And then I can do the same thing for z. Does that make sense? Okay. What about the graphical method? So if I'm choosing a graphical approach to solving a problem, what I realize is my kinematic equation is actually describing some kind of addition of vectors. So this is a vector right here, V naught. This is a vector, A times T. What is this kinematic equation telling me to do? It's telling me to add the initial velocity vector to this vector and then get my final velocity out as a result of that. So I can make a diagram of that vector addition. And if I draw the diagram, I might be able to use geometry to solve the problem, right? Let me show you an example of how that would work, okay, using the same equation. Okay, so let's say this is the kinematic equation we're dealing with. Okay, how do I represent this equation graphically? How do I draw a diagram of the vector addition that's going on here? Okay, well, The specifics of what this diagram looks like depends on the problem. So v naught, the initial velocity, could be anything. A, the acceleration, could be anything. So I'm just going to show you an example. Okay? But generally what we're going to do is we're going to take the initial velocity vector, v naught, and then draw it tip to tail with at, because I'm adding two vectors. When we show that on a diagram, we use the tip to tail method. So let's say that this is my v naught vector, just totally randomly picked. But let's say that's my v naught vector right there. So I'll draw it on a diagram first. And notice, the velocity could have an x component and a y component, generally speaking, if we're in xy, in this xy plane. Let's say my acceleration is oriented at a different angle. Maybe it's kind of going off at a steeper angle like this. So my vector at is just pointing in that same direction. Remember, if I have a vector a and I multiply it by some scalar, like time, I still just get another vector pointing in the same direction. Okay? So there's v naught and at connected tip to tip. The resultant vector is what appears on this side. That's my final velocity. So everyone, explain to me, how do I draw the resultant vector? How does this work with the tip to tail method?
From the origin to the end of the acceleration.
So we start here, and then we end here. That's going to be my final velocity. Okay, so this is geometrically what's going on in this equation. And again, I chose these directions randomly, but you hopefully see the idea behind it, right? So if you prefer to use geometry to solve a problem, you could use some fact about triangles that you know to work it out. Okay? So the last thing I want to show you is this. Let's take our v naught vector, and let's think about what its x component is. That would be what we get when we project that vector onto the x-axis. So hopefully you can see that this right here is v naught x. All right? Let's do the same thing with my second vector, at. Let's project that onto the x-axis, and we get this. So what I would call this projection is ax times time. It's basically the x component of my acceleration times time. Notice that this exactly matches the x component of our resultant vector, doesn't it? Because if we project our resultant vector down, it goes all the way from here to here, right? So that gives us Vx, our final velocity in the x direction. So hopefully you can just visually see, right, that Vx equals v naught x plus axt. I showed you that before, right? We can break this equation down into an x equation. If I did the same thing on the y-axis, guess what? We'd have a y equation for this. So that's where this idea of being able to write down a separate equation for each direction comes from. Okay? So hopefully that's clear. So yeah, let's do it on the y-axis. Forgot I had this. So there's v naught y, there's ayt, right? And then there's vy. And that's where our separate x and y equations come from. Okay. Just want to remind you about some facts of geometry. Maybe you've seen this recently, maybe it's been a while. The law of sines and cosines, okay? So basically, if we add two vectors together graphically, so two vectors are added tip to tail, then I draw the resultant. The general shape that we get is some kind of triangle, right? So if we're going to solve a problem this way, it's important to just remember some facts about the geometry of triangles. So here we're going to be as general as possible. We're not going to assume it's a right triangle or something special like that, just a general triangle. So in this picture, what we're going to do is label the sides of the triangle A, B, and C, lowercase a, b, and c for sides. And then for angles, we'll use uppercase A, B, and C, and there will be sort of a correspondence, right? Like angle A is the one that's across from side A, angle C across from side C, right? So what does the law of sines have to say? The law of sines says that side A divided by the sine of angle A equals side B divided by the sine of angle B, and then same for C, right? So this ratio just is the same regardless of what side of the triangle you choose. That's the law of sines. Is this familiar to everybody? What about the law of cosines? So this is an equation that says side length C squared equals side length A squared plus side length B squared minus 2AB times cosine of angle C. Okay? So depending on the situation, you might want to use either one of these relationships. Okay? We might just pull them out to solve a problem at any point in time. By the way, does this one look kind of familiar? What does this resemble to you? Yeah, it's just like the Pythagorean Theorem plus this extra bit, right? So it turns out the Pythagorean Theorem is just a special case of the law of cosines. If you just set angle C to 90 degrees, you'll get rid of that last term, and then it'll be C squared equals A squared plus B squared. Okay? So the Pythagorean Theorem applies to a right triangle where this angle is 90 degrees, but this is more general. This applies in any case. Okay? We're good on that? Okay, so let's do an example where we actually put our two-dimensional kinematic equations to use. So here's what's going on. Let me explain the scenario, and I'm going to show you an animation too, because it's a little hard to picture without that. Okay? So we have a rocket drifting in empty space with a speed of 25 kilometers per second. At t equals 0, the thrusters of the rocket are fired, and what that does is it provides a constant acceleration of 1.5 kilometers per second squared in a direction that is 35 degrees relative to the initial motion of the rocket. So the question is, how far does the rocket move after 12 seconds of that type of acceleration? Now this is a perfect example of how to use our 2D kinematic equations, because this motion is not just going to be along a straight line, because our velocity and our acceleration are actually at some angle with respect to each other. And it's important to realize that in general, your velocity and acceleration can be at any angle with respect to one another. Okay? So we're imagining in this case that it's 35 degrees. Okay. So this is what it would look like. I'm just going to show you an animation. So here it is. We have the rocket moving like this, and then the thrusters are fired. Okay, so its initial velocity is going off at a diagonal like this in the animation, but its acceleration is straight to the right in this animation. So we're initially drifting at a constant velocity until we fire the thrusters, and then we start to accelerate. Does that make sense? Okay. So let's work it out. So I want to show you both methods. I want to show you the algebraic way of solving this problem, where we just write a separate x and y equation, solve it all just using numbers, and then the graphical approach. And then we'll take a poll. Let's see, which one you like better as a class. Okay? So let's set it up. Let's start with the algebraic approach. This is probably a little bit more familiar to everybody. So let's just draw real quick what's going on. I'm going to set up a coordinate system where this is x, this is y. And let's put the origin of our coordinate system as the starting position of the rocket. Okay? So what we saw in the animation is the acceleration was going straight to the right like this. So that's my vector A. But my vector v naught was going like this. That's my initial velocity. This angle right here, I'm going to call that theta naught. We know it's 35 degrees, but I'm just keeping things symbolic for now. Okay? Am I writing big enough? Can you all see that in the back? Okay. So here's what I'm going to do. I'm going to write down what my initial position is, what my initial velocity is, and what my acceleration is in xy component form. And then we can actually just plug all that into our kinematic equation. Okay? So what's our initial position here?
0.
Yeah, it's just 0, 0, because I'm at the origin. So I write that as r naught equals 0 I hat plus 0 j hat. That's easy. What about the initial velocity? So I'd have to take this v naught vector and break it down into x and y components, right? Let's do that. V naught x. That's going to be the magnitude of my velocity. So that's how fast we're initially moving times cosine of our angle. That's going to give us the x component. So let's put in the numbers. We have 25 kilometers per second, cosine of 35 degrees. Someone crunch those numbers for me real quick. And while you're doing that, let's write down what the y velocity, y initial velocity is. That's going to be magnitude of v naught times sine of theta naught, which is 25 kilometers per second, sine of 35 degrees. So that's how we get the x and y components of our initial velocity. Does anyone have the x component? I'm getting something a little different. Yeah, it's 20.5, 20.48. I'll just keep an extra digit. We'll round off later. 20.48 kilometers per second. And then what about for y?
14.3.
Yeah, I'll keep another digit, 14.34, and then we'll round off later. Kilometers per second. Okay, so we see how that's how our initial velocity breaks up into x and y, right? So the last thing, because this is another ingredient in our equations, let's do acceleration. This one's pretty simple actually, because I have an x component for my acceleration and a y component, but which one of these is going to be 0? The y component, right? Because this points entirely along the x-axis. So that means it doesn't have any y component. And the x component is just the magnitude of the vector, which is 1.5 kilometers per second squared. Okay? Good on that? So, let's write down a kinematic equation that's going to be useful here. The kinematic equation that I'm going to use is R equals R naught plus V naught T plus 1/2 AT squared. But then I'll remember that this vector equation is really two separate equations in disguise. I'll have an equation for the x position and an equation for the y position, which I can write down separately. That's what we're going to do because this is the algebraic method, of course. Okay? So if I take the x component, that would be x, final x position, equals x naught, initial x position, plus v naught x times t, plus 1/2 ax, t squared. So hopefully that's clear, how we can just write this as our x component. Now I'm just going to put the numbers in. What should I put in for x naught? Right here. I should put in 0 because we're just starting at the origin, right? What should I put in for v naught x? I should put in this value that we calculated, 20.48 kilometers per second. The time is 12 seconds. That's just what we're asked about is 12 seconds later. So I'll put in t equals 12 seconds. And then I have a half times ax, which 1.5 kilometers per second squared. And then take t and square that. So 12 seconds, square that. Okay, what does this tell us? So someone punch that into the calculator, see what you get. .76 units are kilometers, right? And we'll actually keep 3 sig figs just to keep track, but we'll round that off later at the end, okay? Now what does this tell us? That tells us that we moved this distance along the x-axis during this motion. Okay, but we don't know how far we moved along the y-axis, so we need to write down a separate equation to get that. For the y component, we have y equals y0 plus v0 yt plus 1/2 ay t squared, right? And again, we're just plugging in everything we know because we set the stage already. So, okay, what am I plugging in for y naught? Right here. Yep, plugging in 0. Just the way we set up our coordinates was to put the origin at our starting point, okay? What about v0y? What should I put in for that? 14.34 kilometers per second, and then that's going to multiply t, which is 12 seconds. And then what do I put in for ay? Yeah, so there's no acceleration in this case in the y direction. So that's a simple calculation. What does it come out to? Sorry, say it again? 172.08. Yeah, 172.08 kilometers. Okay, so now we know both how far we've traveled in the x direction and the y direction. So we should be able to find just the distance, right? But let's actually make sure we can visualize this. So the vector r has an x component and a y component. This is our final position relative to where we started, right? So we found x, and then we found y. I start here, and I end here. How do I find just the straight line distance between those 2 points?
Pythagorean Theorem?
Yep, Pythagorean Theorem. The way we write this is the magnitude of this vector r, that's what we really want to know, is equal to the square root of its components squared added together. So x squared plus y squared. So we'll put in what we know. That's 353.76 kilometers. We'll square it, add it to 172.08 kilometers. We'll square it, and then put that under the radical. And let me know what you get for this.
393.3.
Yeah, so I'm getting like 393.3. So when we round it off, it's just 393, right? So that's our final answer. So that's how far you moved in 12 seconds. Okay, hopefully you see how this works. Let's try this the other way. That's the algebraic method. We write a separate equation down for the x and y motions, and then we put it all together at the end. Let's do this the graphical way. Okay, so we're actually doing the same problem, and we're just going to see that we get the same answer. Okay? So here's the graphical method. So we're dealing with the same equation, okay? R equals R naught plus V naught T plus a half AT squared. We're still dealing with this equation. But this time, I don't want to break it down into components. Instead, I'm going to draw some kind of diagram that describes what's going on in this equation, okay? Let's just, like we did before, suppose we're starting at the origin, which means the R naught piece goes away. And then we'll take it from there. So what are we adding together in this equation? We're adding together a vector, v naught times t, and then we're adding that to half at squared. So what direction is this vector pointing in, the v naught t vector? It's pointing in whatever direction my v naught vector is pointing in, which is kind of at an angle like this, right? 35-degree angle, going like that. What direction is this vector pointing in? It's just pointing straight to the right, because that's the way my acceleration is going. Okay, so I just want to not necessarily measure it out exactly, but to show that I'm adding these two vectors, and I have some sense of which way they're pointing. Okay? So here. I'm going to add these two together, tip to tail, in a diagram. So let's draw the first vector. My v naught vector is kind of going into the first quadrant like this. So that would be v naught t right there. My acceleration vector is going to the right. So this would be 1/2 at squared. That whole thing is a vector. And when I add those two tip to tail, the resultant vector I get is r. So that's this vector, isn't it? Okay? So now we have a triangle. And I'm just going to use facts about geometry to do the rest of this. If I know how to relate the lengths of the sides in this triangle, that should be all I need. Okay? But before we do that, we need to get a sense of what some of the angles in this triangle are. Okay? So here, I'm going to draw just a little kind of dashed line right here. What is this angle right here between my velocity and acceleration starting off? What angle is this one that I'm pointing to?
35?
That's the 35-degree angle, right? That's the angle between our velocity and acceleration to start off. Now that angle is not actually in the triangle, so how about we label this one instead, this really obtuse angle inside of the triangle. What is that angle?
145?
Yeah, you see that? They add up to a straight line. So they have to add up to 180. 35 plus this is 180. That means it's 145. We agree? So now I have a triangle where I at least know one of the angles. Okay? So let's do this. Let's call, I'm just going to label things. I'm going to call this side A. I'm going to call this side B. And then I'm going to call this side C. Okay? Okay, what are the lengths of each one of those sides? Well, the length of side A is just the magnitude of the first vector that I drew. Remember, length in terms of a vector is referring to magnitude, right? So I have magnitude v naught t. So again, I'm not interested in breaking this into components. I'm just interested in finding the magnitude. So what I would do is take 25 kilometers per second multiplied by 12 seconds. And what would that give me? Just 25 times 12. Yes, 300 on the dot. We'll keep the third digit as significant because we have 3 sig figs in each one of these numbers, okay? That's going to be kilometers, by the way. So the length of this is 300 kilometers. Okay, what about vector B? That's my 1/2 at squared thing. the length of that side is magnitude of this vector. So again, just interested in the magnitude, not the components. This is a half times, take our acceleration, that's 1.5 kilometers per second squared, and then multiply by our time squared. So can someone do that calculation for me?
108.
Yeah, that's 108. Okay? Okay, what about side length C? That's the magnitude of our vector r. And just remember what this vector is doing. It takes you from the starting point to your ending point. Okay? And what we want to know is the distance between the starting and ending point. That means we want to know side C, right? So if I know side A, I know side B, and I actually know angle C, so that's big C, that's 145. Which one of those facts about geometry can I use here? Law of cosines. So we're going to pull out the law of cosines to solve the problem. Law of cosines, let's just write it out. That is side C squared equals side A squared plus side B squared minus 2AB cosine angle C. Okay? So if we're looking for side C, we just square root both sides, correct? And we'll plug in all the numbers. Side A, 300 kilometers. Square it. Plus side B, 108 kilometers. Square that as well. Minus 2, multiply A and B together. That's 300 kilometers times 108 kilometers. And then finally, multiply that by cosine of C. That's our 145-degree angle. Okay, so someone punch that into your calculator. Tell me what you get.
The same answer, 393.3.
You get the same answer. Okay. So that's the graphical way to do this problem. This is the algebraic way. I mean, it looks like we did slightly more work if you're just counting the length of the page, right? With the algebraic way. Which one did you prefer? Who thinks of this comes more naturally with the algebraic approach, the first way we did it? Okay, who prefers the other approach, the one we just did here? Okay, who hates both of these? Okay, yeah, of course. All right, so it's really up to you. I'm not going to say which one of these is correct. Whatever works for you. All right? Okay, there's one last problem I want to do, and we're going to do it together real quick. Same situation. We have this rocket. We know its starting velocity, and we also know its acceleration. We're not asking about how far it's traveled in 12 seconds. We're not looking for a distance. Now we're looking for a speed. How fast is it moving after 12 seconds of acceleration? That's what we want to do for this last bit. So I think more people said they prefer the algebraic way. So let's do that first, and then maybe if we have time, we'll do it the other way. All right, so same question, just the thing we're solving for now is speed. Okay? So real quick, let's do that. So I should be thinking that I want a new kinematic equation, and that will be v final velocity equals v naught plus at. And what I really want to know is the magnitude of my final velocity. That's what we call our final speed. Well, one way I can get this is to get the x and y components of my final velocity first, and then take the magnitude of that vector once I know its x and y components. So with that approach, what we'd say is, let's break this kinematic equation down into an x component and a y component. So for my x component, I have Vx equals V naught x plus AXT, right? And actually, let's just plug in what we know. We did some of the legwork for this already in the previous example. What's V naught x? Now that one is not 0. Yeah, that's 20.48 kilometers per second, if you remember. Okay? What about AX? What was that equal to?
1.5.
That was 1.5 kilometers per second squared, and then t is 12 seconds. So if you work this out, what do you get?
$38.48.
38.48 kilometers per second, I agree. So that's the x component of your velocity at the end. What about the y component? Well, Vy equals V naught y plus AYT. So what was our V naught y value?
That was here. Was it here?
That was a 14.34. So again, we worked that out previously. Kilometers per second. And what's AY? That's the one that's equal to 0. So what this is telling us is because we have no acceleration in the y direction, our velocity in the y direction doesn't change at all. That makes sense, right? There's only acceleration in the x direction, so that velocity is changing, but not this one. All right, what's the speed then? Speed is the magnitude of the velocity. That's how this works. And that's the square root of Vx squared plus Vy squared. So plug in these values. We have 38.48 kilometers per second. We want to square it, plus 14.34 kilometers per second. We want to square that as well. And then put the whole thing under the radical. And what does that give you?
41.06.
Yeah, it's 41.1 is what I'm getting. Kilometers per second. Okay, so we've sped up some amount, right? So let me just outline how you do this the other way. This would be the algebraic method, right? The alternative solution is to start with our equation that we wrote down at the very beginning and draw some kind of diagram showing this vector addition that's going on. So it's telling us we take our V naught vector, and then we add to it our vector AT, and then we get our final velocity vector out. So our V naught vector goes like up and to the right like this. Our acceleration goes straight to the right like this, so that's AT, added tip to tail. And then our final velocity is the resultant of that addition. You can actually show that this angle is still 145 degrees, just like before. But the side lengths now are a little different because we just have a different equation. But if you work it out where you solve for this long side, that's the magnitude of this velocity, you'll end up with this answer. But we don't have enough time to go through that, but that's roughly how it would go. Okay? So that's it for today. See you in lab.